on function. Okay, you may start, please.
Yeah, thank you, everyone. So my name is Jingran Zhai, and in my talk today, I would like to introduce an application of a generalized Chernoff approximation in the context of what is called bicontinuous semigroup. And I would like to apply this to a problem in mathematical epidemiology. So the structure of my talk is as follows. We will first introduce the epidemic model we're going to work with and the definition of the extinction time problem and its epidemiological motivation. And next, we want to show how we can transform the extinction time problem to a degenerate PDE problem. And lastly, we introduce the concept of bicontinuous semigroup and give our main result. So for the first part, we talk about the epidemic models. So one way,
are you showing the first slide or not?
Yes. Because, is it not working?
Okay. Just I want to check that it works. Like, can you show us the second one?
I mean, I'm on page 4 right now. So.
Oh, we only see the first one.
Right.
You should probably exit full screen.
Let me.
Okay. Now we see page 5.
Yeah, this is sharing. So. No, yeah, I think I have a sharing problem when the screen is on full size. So
I think you should not use full screen. Just
let me.
It will be okay.
Sorry about that. Let's start again.
For example, you can send me your PDF. Oh, perfect.
Okay, now.
Sorry, let me see. Yeah, so luckily. So yeah, let's start from here. So let's talk about the epidemic model. And one way of modeling the course of epidemic is by divide the target population into different groups and track the size of each group. And this is what we call compartmental epidemic models. So we assume that the target population is closed, which means it has nobody moves in and out of the population, and the size is of a fixed number n, and homogeneous mixing, which means that everyone is considered to be identical. So the simplest model of this type is called SIS, which is named after the route a typical patient would take. This model is for infectious disease with no significant immune period. It divides the population into 2 compartments, S, which consists of individuals who are currently healthy but can get infected, and I, which consists of individuals who are infected and can transmit the disease to other people. Each individual in S compartment contacts another person uniformly at random and contract the disease at rate lambda O if the other party is infected. And every individual in compartment I recovers and returns to compartment S at recovery rate 1 independently. So when we with the stochastic version of SIS model can be written as a one-dimensional continuous time Markov chain valued in integers between 0 and big N. So here is the transition rate of the stochastic SIS models. In this setup, the parameter lambda O corresponds to the basic reproduction number in epidemiology. So the basic reproduction number essentially describes the ability of a disease to prevail when it's first introduced into a population. So our focus is SIRS model. So the property of SIRS model is relatively well studied, but there are many diseases that actually has waning immunity and thus does not fit for SIRS model. For example, influenza or even COVID, really. So this is why it's important we study the type of model is called SIRS. So compared to SIRS model, the transition from compartment S to I is the same, but we add a third compartment R, which consists of individuals with immunity. And when an infected person recovers, it moves to compartment R, and each individual in compartment R loses immunity independently at rate gamma O and becomes susceptible again. If gamma O equals to 0, which means everyone has permanent immunity, and this model is then called SIR model. So formally, like before, we can define the stochastic version of SIRS model as a two-dimensional continuous time Markov chain with a two-dimensional parameter space. We know that this model will almost surely reach absorption at 0, 0. Therefore, we can define extinction time as the time it takes for the size of the infected compartment to reach 0. So in mathematical epidemiology, one question we ask is what is the scaling behavior of the distribution of the extinction time and how it changes with different parameter and different initial states of the model. In other words, we hope to find the appropriate shift and scaling function depending on n, the big N, such that the scaled extinction time converges to a non-trivial distribution. We also hope that our scaling is as explicit as possible because deriving the distribution of extinction time can be numerically very expensive. So by the last 2 or 3 years, the extinction time problem for SIS model is well studied, but not so much for SIRS model, which is why we're looking into it. One way to get an intuition of how SIRS model behave is by looking at its corresponding deterministic model. Because, so the deterministic model is as an ODE system, because it is a good approximation for the stochastic version on compact time intervals in this sense, in the parenthesis. So the long-term behavior of this ODE system shows that we expect to see the criticality at lambda O equals to 1 and gamma O equals to 0. And when lambda O is larger than 1, the ODE system tends to a non-zero equilibrium, which corresponds to an endemic in the population. And when lambda O is smaller or equal to 1, the ODE tends to a disease-free state, which means the disease goes extinction in the population. And when gamma O equals to 0, i.e. the SIR model, the behavior is different. We, in this case, compare how many people ended up getting infected comparing to how many people was infected in the first place to see whether it's above or below criticality. So from this analysis, we would expect that the SIRS model would show the epidemic to prevail for a long time before extinction if it is above criticality 1. And the epidemic is expected to extinct quickly if lambda O is smaller than 1. And this is indeed the case. We found that for subcritical case, the extinction time is of the order of log n, and it can be written as in this form, and we know k and the distribution of G explicitly. And when the SIRS model is supercritical, Stochastic in 2003 shows that essentially the model will approach what we call quasi-stationary distribution very quickly, and then stay there for exponential to n amount of time, and then move to extinction. So in the case of SIRS model, researchers soon realized that the approximation, like in the previous slides, will no longer be accurate if lambda O is very close to 1. And this motivates us to study the near critical behaviors. So, which means the parameter tends to criticality as the population size n tends to infinity. And this is important in epidemiology because when there's a mutation in the pathogen strain happens, or if there is a eradication campaign launched in the community, then it may actually push the basic reproduction number R0 across the criticality. After some careful examination, researchers find that for the case of SIS and SIR models, there is a domain around the criticality that divides the near critical regime into 3 parts. And so the middle part, which is called critical regime, behaves uniquely, and the subcritical regime actually mirror what we would find for lambda O far away from below from 1, and so does the supercritical regime. So for SIS and SIR model, we find the width of the critical regime is actually of order n to the power of -1/2 and n to the power of -1/3, respectively. So now the question is, can we observe something similar in the stochastic SIRS model? And so far the answer is partial, but essentially, yes, we believe we can find something similar, but slightly more complicated for at least the subcritical and critical regime. And this motivates, we are gonna talk next about identifying the critical regime and then investigate the behavior of extinction time within this regime. So in the next part, we talk about how we transform the problem in critical regime to a PDE. So to identify the critical regime, we perform a scaling, as in the first item, in both parameters and on the time and space of the Markov chain. And this scaling is determined by matching the order of infinitesimal linear and quadratic size of jumps. And we call this scaling the critical scaling. And the critical regime is when both parameter and the initial state of the Markov chain is of the same order as the critical scaling, as shown in the third item. Of course, then the extinction time will also be scaled accordingly. So as in the first line, and then we can see that the extinction time in the critical scheme critical regime is of the order n to the power of 1/3. So next, we want to see what is the distribution of the scaled extinction time. The first result we have is that we can find the scaled Markov chain weakly converges to a limit diffusion, and we can connect our scaled extinction time Tn to the hitting time of this limit diffusion. So this is the sketch of proofs of the previous statement. So just a quick comment. So what is different here is that the limit generator of this diffusion is degenerate on the entire R2 plus, and we need to first show that the limit diffusion is indeed well defined. And this is done by applying the standard localization argument to a result from Brunig 2013. And after that, we prove the convergence to the diffusion. And next, we need to prove the convergence of the extinction time by showing that the sequence has a tendency of approaching downwards towards 0. So by the standard argument, for example, Feynman-Cat formula, we can write the tail distribution of this hitting time of the diffusion as the solution to a PDE problem. So here we see that the operator in this PDE consists of the second order part, which is actually associated with square Bessel process of dimension 0, and a first order part, which we denoted by L and H respectively. And this motivates us to consider H to be a perturbation added to L. Then we go to the last part, the main result. So we first introduced the definition of bicontinuous semigroup. And the motivation of this definition is that in application, especially Markov processes related to populations, the semigroup we are interested in may not be strongly continuous in the Banach space that we are interested in. For example, Austin-Uhlenbeck semigroup is not strongly continuous on the space, the space of continuous bounded function on Hilbert space H, equipped with the supreme norm. So to deal with this situation, we would like to introduce a coarser topology so that we can still take advantage of the strongly continuous property. And this is essentially the idea of bicontinuous semigroup. So the space we work on is as such, where we have a Banach space and we introduce a coarser topology rho, and then it has to satisfy these three conditions. So for our application, we work with the space of bounded continuous function on R2 plus with a continuous extension to the boundary, equipped with the supreme norm, and with a coarser topology, which we choose the compact open topology and represent it with some UCC. Then the definition of the bicontinuous semigroup is analogous to what we know for the strong continuous semigroup, except for we define the strong continuity in the sense of this coarser topology, and we also require locally bi-accurate continuity in this sense. So the generator resolvent and the generation theorem for bicontinuous semigroup are also developed by Kuhnemann in her PhD thesis, analogous to the classic results, which you can find in her thesis. But we will only introduce the theorem that we're going to use, which is the generalized Chernoff product formula. So comparing to the classic theorem, we would require this locally bi-accurate continuity property of the operator family, and then yeah, essentially we can relax the uniform the norm convergence to the convergence in row topology for generator A. So for our application, and then yeah, so for the function, the operator Vt is called Chernoff function or Chernoff equivalent. And so how we construct Vt is by considering the second order operator L and the first order operator H separately. So for L, because the transition probability of square Bessel process is explicitly known, so we can actually have a nice explicit description of the semigroup generated by L in this form, and we know the function G, and it contains a modified Bessel process, modified Bessel function. And for the first order operator, we find Wt, which is essentially the Chernoff function for the first order operator H. And we use this instead of the semigroup form because the semigroup form cannot be written explicitly. And we can show that Wt has the property of locally bi-accurate continuous and bi-accurate continuous. And we define Chernoff function Vt as such. So by applying the generalized Chernoff product formula, we have the final statement. And this allows us to write the tail distribution of the extinction time as the limit of a iterated integral. And so this allows us the potential for analytic and numerical experiment for the future. But for our case, this iterated integral is still slightly difficult to calculate by hand. But if the first order operator is simpler, then we can actually calculate the iterated integral explicitly. So we are showing an example here with the same second order operator, but a simpler first order operator. And in this case, we can calculate everything explicitly and get the solution in this form, so which shows which is a very nice way of getting an explicit solution. Yeah, and that's all I would like to talk about today. Thank you for listening, and this is my reference.
Okay, thank you for your talk. We have some additional minutes, and for that reason, do anyone have any questions or not? I think that in case your work is about the applications of this whole thing, could you please repeat the main implications of those formulas? Have you found something interesting about the epidemics?
For the final result. Yeah, I think basically, so the entire premise is actually two parts. One is find the correct scaling, and then we like to have a good approximation of the scaled function. So for now, we can write this in a iterated integral form. So it gives us the potential of studying how different parameter influence the extinction time. So for this part, we don't really have a direct knowledge of how this is exactly understood in the context of epidemiology. Yeah, so it's basically we're just trying to display as much information as possible so that practitioners can look into it.
And do you somehow prepare the numerical experiment for this stuff or not?
For this part, so I tried it, but basically I think it like in the previous talk, the numerical code needs to be done very carefully, especially our integration is in from 0 to infinity. So we need to actually approximate it very carefully. For example, the package that is ready to use in MATLAB or whatever need to be tuned carefully or even rewritten to actually make sure we don't get too much error when we iterate many times. So I did a little experiment and it's not very successful. It's much easier to, so we did a lot of experiment in the subcritical case in terms of simulation and calculate the asymptotic distribution numerically. But for this part, we don't have anything done yet.
Mm-hmm. Well, you can estimate the speed of convergence with the result from the previous talk.
Yeah, exactly. I think that's actually a very interesting thing to see, and it's definitely, I think it's very important for this kind of application to have that estimate.
The
so that it can
is on the archive.
Yeah.
The preprint is on archive. You can use it.
Yeah, definitely. Thank you.
But by the way, this formula looks more like Trotter formula, and we know some things about the convergence of Trotter type things, like there is the Suzuki Trotter formula in which we can guarantee that the convergence is greater than this type. Can you comment on that or not?
I think so. I'm not very familiar with the sort of the rate of convergence of this problem. So, but in terms of Trotter, so the only difference, so why I don't use Trotter is because we have to use something that's not quite a semigroup. I think that just makes it deviate from Trotter formula. So become you have to use Chernoff. Yeah, so I think definitely a good companion to this conclusion is to actually investigate the rate of convergence and the other properties of this approximation. Yeah.
Okay. Well, are there any additional comments or questions?
Let us thank the speaker.
Yeah.
Thank you. Thank you.